During this step of our workshop, we add a USB host stack that connects a mass storage device. It is our USB stick, which we are using on the ST Discovery Kit. We will also add the CMSIS driver for the USB host interface and the file system that controls the files on the mass storage device. At the end of this step, the ASCII content of an existing text file from the USB stick is displayed in a memory window of the debugger. Open the runtime environment and select from USB the host MSC mass storage class. With this selection, I'm getting 3 additional requirements. The USB core is the core component of the USB stack. Since I'm using the host functionality, I need also the USB host component. And finally, the mass storage device uses a file system to access the content. Well, you can select all these components manually if you prefer that. But with a click on Resolve, the required components are selected for you. With this step, you have actually added many components, including the file system with a USB drive. But the system cannot decide the USB host driver for you, since the ST device provides 2 physical connections, the USB high-speed and full-speed interface. For using the right interface, you should explore the hardware of the ST Discovery Kit. The USB connector on this kit uses the on-the-go high-speed peripheral via the on-chip full-speed PHY. I know this sounds scary, but actually you just need to select the right driver and configure it. In this case, the CMSIS driver for the USB host high-speed peripheral is needed that we will configure in the next step. Our selections in the RTE window did include several new project files. We have files now for the CMSIS driver, the file system and the USB component. As explained in the related documentation, we need now to configure each component. If I miss a configuration, the system will show several errors during compilation with hints to the configuration settings. All CMSIS drivers are configured with the RTE device header file from the device framework. Open this file and enable the USB on-the-go high-speed interface. Select as PHY interface, on-chip full speed and configure the VBus and the overcurrent detection pin. Note that the name is driver USB H1. Now I need to connect the USB host middleware to this CMSIS driver. To configure the USB component, open the file usb-h-config0. This file configures various parameters, but we use defaults for most of them. Important, however, is the connection to the hardware. I will therefore select the driver USB-H1 to interface with our CMSIS driver. I can use defaults for the remaining configuration options of the USB component. The file system is configured with the file fsconfig. Again, I can use defaults for most of the options, but I should assign the current drive to an existing drive ladder. In our system, we only have one drive, the USB mass storage device that uses the drive ladder U0. As documented, the middleware components have additional resource requirements for the RTOS system. I need therefore settings for these requirements in the CMSIS RTOS configuration file. So I open rtx-conf-cm.c. The file system needs a default thread stack size of 1000 bytes. The USB component runs on a user-provided stack. Therefore, I set the number of threads with the user-provided stack to 1 and the related total stack size again to 1000 bytes. This completes the configuration of our software components, but actually we are not doing anything with them. Well, we will use a RTOS thread to read files from the USB stick. That's why I add a CMSIS RTOS thread user code template. This adds the file thread.c. I might change this thread name to make it more descriptive, but for our example we just use the default naming. To access the USB mass storage, I use again a template file. This adds the USB-H MSC source code. This file describes even how to access the USB drive, and next I will add the relevant portions to the RTOS thread. Therefore, I open the file thread.c, where I add code to the thread function. We now start this thread using the init thread function. And this call has to be added to main.c. Now, our application code is complete and we can build the project. Again, we are checking if our code works. A breakpoint on the thread function verifies that the thread executes. I can single step to check the USB initialization. Another breakpoint to fopen can be used to verify the file access. Once you connect the USB stick to the discovery kit, the drive will be mounted. Then open a memory window and display the file buffer. Once you single step on the application, you can watch how the file test.txt is read from the USB stick. In our case, the content of this file is the string Kyle middleware and CMSIS pack. Let's explore now the new RTOS threads that we have added with our middleware components. The System and Thread Viewer shows two new threads. Access to file system works via the function thread, and as you remember, we did not change the default name. And the function USB-H0 core thread is running the USB host stack. On the system, you can also see the stack adjustment, which is now 1000 bytes default stack. We complete step 3 of our workshop by taking a quick look at the event viewer. Here we see the timing information of our new threads. Next, at step 4, we will add the graphical user interface to our project.